Okay, and we are recording. So hope everyone is well, and we will continue with modular arithmetics. This I forget right now, but I think it's section 9.5 right now, or 9.6 or so, and it is. Are we getting homework? Yes. So I will release a homework right now. I got completely entangled in grading test 2, and I forgot about the next homework. Okay, sorry about that. So I will release it after this lecture. Okay. Okay, thanks. And it's section 9.5. Okay, so okay, let's recall where we were. So for any positive integers, or rather an integer a and a positive integer b, you can define an integer division of integer a by a positive integer b, and it's defined using two integers, a quotient and a remainder. A quotient is basically a floor of rational division of a divided by b, and the remainder r is the remainder of that division. So basically you take the nearest multiple of the divisor b, the nearest but no larger than a, so it's the nearest from the left side of the scale, and the remainder is the difference between the original integer and that multiplicity, or and that multiple of the divisor. Okay, so we introduced the concept of greatest common divisor between two integers, right? We said that any integer has a unique factorization, and therefore you can look at the common at the intersection of the factors that are common to both integers, right? And the product of this intersection of factors is the greatest common divisor between the two numbers. And it will be very useful in several crypto systems to be able to compute this greatest common divisor and to verify, for example, whether it does not exist. Okay, so that the two numbers are relatively, what we call relatively prime, because they don't have factors in common. Okay, but as we said last lecture, computing factors in general, there is no efficient algorithm that would do so. So the general algorithm to do so is exponential time, exponential in the description, in the length of a and b. Okay, encoded either in decimal or binary, it doesn't matter, that's just a constant scale. So, but there, surprisingly, there is actually an easy algorithm to compute common factors between two integers. Okay, and in fact, this algorithm was known already to ancient Greeks, to Euclid, and it's called Euclid's algorithm. So it comes from the following two facts, this algorithm, okay? And actually it will be a recursive algorithm. So and you will see other recursive algorithms actually in this, even in this section, which hopefully gives you a feel that like there is a purpose to learning recursion and recursive algorithms. So here is one observation. If there's two integers, a greater than b, and some divisor, an integer that is at least 1, then if D is a common divisor between A and B, so D is a common factor, the common divisor, because it could be a product of several prime factors, but then it will also be a divisor of A mod B. In other words, of a modular reduction of A divided by B. Okay, so again, what is the A mod B? It's the remainder of the integer division of A divided by B. So that's this remainder here. Okay. Okay. So this will be, this is kind of a hint for how you might compute common divisors of A and B, because whatever is a common divisor of A and B, let's call it D, turns out to be also a common divisor of B and a number that is much smaller than both of them. Well, it might be, it's definitely, well, I don't want to say much, but because that depends on the case, but it is definitely smaller than B, because a remainder of integer division of A divided by B must be smaller than B. And it's also no larger than A, right? Because the only case where this can be as big as A is if A was smaller than B, in which case A mod B is just A itself. But that's not the case. A was a larger thing than B. So therefore, this is it's smaller than B, so it's definitely smaller than A. So that's a basic recursion right there, a possibility of recursion. So let's check that this fact is true. Okay, I'm looking at the chat messages, but I think that, okay, yeah, it looks like concatenation, people said. No, this is integer division. And so boom, it's the same vertical sign. I believe we have 4 different uses of it in this class. Okay, you can write on Piazza. What do you think these 4 are? Please do. Okay. And yes, one of these 4 is concatenation of strings, and one of them is to signify that integer D divides integer A. So these are integers here. All right. So okay. So let's look why this is true. So look, the definition of A mod B is that it is an integer R that satisfies the following. First of all, it's some integer between 0 and B minus 1. Secondly, there exists some integer quotient which makes this true, this equation true. You can rewrite this and just put QB on this side, right? And in which case R is, it's the same equation, says that R must be expressible as A times some multiple of B, okay, some integer multiple of B, and R must be in this range. And we argued that this uniquely defines R. Okay, so let's take this, remember this one, and let's show that this is true. So I have it here. So look, if D is the divisor of A, that means that there is some multiple of, that A can be expressed as some multiple of D. That's what D dividing A means. It means that A is a multiple of D. If D divides B, then that means that B is also a multiple of D. Some other multiple, okay? And we don't care what that is, but that's just denoted with some integer, like M here and Q here. Now, A mod B is defined using these constraints. So in particular, it must be A mod B is always expressible as A minus some sufficient number of multiples of B, where sufficient means whatever, so that the R gets into this range. Okay, so for our purposes, what we need is just this part, that R is a linear function of A and B. Okay, so R, which is A mod B, the remainder of integer division of A divided by B, is this function. So it's A minus some multiple of B. And now, because both A is a multiple of D and B is a multiple of D, so I can rewrite this, and clearly I take M and minus QK, group them together, and this thing turns out to be a multiple of D. Okay, so it's by linearity, because the remainder is a linear function of A and B, namely this one. So if A is a multiple of D and B is a multiple of D, then so must the remainder be. Okay, so far so good. Let's do fact 2. So that fact 1 tells you that if something was a common factor between A and B, then that something also necessarily have to be a factor, a common factor between B and something smaller, and A mod B. Okay, so Euclid's algorithm will basically recurse, and when it's asked to compute the GCD, greatest common divisor, between A and B, it will recurse and instead run itself on modified inputs, which are B and A mod B. And by this fact, you will know that you couldn't lose any common factors doing that. Whatever was a common factor between A and B must also be a common factor between B and this reduced integer here. But the second question is, okay, you didn't lose any common factors, but perhaps by modifying this question, the question of what's a common factor between A and B, to the new question, what's a common factor of B and A mod B, perhaps you created some new factors. Well, that's the second fact. No, you didn't. Okay, because if something is a common factor of this reduced number, A mod B and B, then it also must be a common factor of between B and A. So in other words, this recursive jump did not create any new factors. All the common factors are therefore preserved. When you, instead of looking at common factors of A and B, you instead look at common factors of B and A mod B. So this proof of the second fact is almost the same as the first one, right? So now, let's just rewrite this equation to the original one. So the remainder, if something is a remainder, then it must satisfy this equation. A is expressible as some quotient number of B's plus the remainder. Okay, so if D is a divisor of this remainder, so therefore of A mod B, which is R is A mod B. So therefore R, the remainder, is some multiple of D. And this again means that B is a multiple of D, right? And because A is a linear function of B and a remainder, this is this function with integer coefficient. So therefore, whatever divides both remainder and B must also divide A, the same as the previous slide. Okay, so taken together, it means that whatever divides A and B, both, also divides B and A mod B. So therefore, the sets of integers that divide A and B is the same as the set of integers that divide B and A mod B, and therefore the largest of the both sets are obviously the same because these are the same sets. The divisors of these two and the divisors of these two are the same sets by this equivalence, because it holds for every D. And therefore, and that's the GCD of these two, and that's a GCD of these two. And that's where Euclid's recursion of Euclid's algorithm come from, right? So here is the Euclid's algorithm. If you're asked to compute a GCD of A and B, you can instead compute and order them so that A is larger than B. You instead can compute a GCD of B, the smaller of the two, and A mod B. Okay, so therefore you get a recursion because you started with two numbers where the larger A and B are in this relation, and you were asked about GCD of these two, and you reduced that to the GCD between these two, which are smaller. So next time, the next level of recursion, right, will be asking about these. So this will be your new A, and this will be your new B, and then there will be your new A mod B, and they will be smaller and smaller and smaller and smaller. So therefore they will terminate. Okay, why would they terminate? Because they cannot be negative, right? No matter what these integers are, first you did it assuming they're positive. And so A mod B and A mod B is always positive. Sorry, or zero, right? So it's non-negative. So this whole chain cannot reach negative numbers, and it's a strict inequality. So therefore it must terminate. But actually, what's the best case, base case, right? So we specified the recursion step, but we didn't yet set, okay, so at some point you must stop, right? What do you answer at that point? Well, there is different ways you can do it, but here is an easy one. If you start with numbers such that B is a divisor of A, then you answer that the greatest common divisor between A and B is B. True enough, right? And that's really the same as to say that if B divides A, another way to say it is that A mod B is a zero, right? Because A mod B is a zero exactly if A is a multiple of B, right? So in integer division, the remainder is zero. And A being a multiple of B is exactly what this says. Okay, so this is the recursive case. When this hits a zero, you answer B. Okay, so here is the recursive algorithm. The GCD of A and B is if A mod B is zero, you return B. That was the base case. Otherwise, you return the output of this algorithm of recursive call to the same algorithm on modified inputs. Namely, the larger integer is B, and the smaller integer is A mod B. And I'm assuming that the algorithm is always called on two integers ordered. So A is larger than B. Okay. I mean, I can just make a first line that says if they're not ordered correctly, I just reordered them. But that just makes this unnecessarily complicated. Okay, so actually this is probably a good moment to run this algorithm on a piece of paper. Hold on. Okay, and okay, and so that not to mess people up who are watching offline, I'm gonna stop sharing now. I think that will do it. Okay, and so again, what's the code? Euclid algorithm. GCD on AB, assuming A is greater than B, is if A mod B is 0, return B, else return GCD of B and A mod B. Okay, so that's a code. Okay, let me see. Do you get?
You're muted, Professor.
Did you mean to mute yourself?
Sorry. Yes. Okay. Thank you. Okay. So so let's run it on some numbers. Okay. So let's say let's take. No, I should have thought of making this example sort of more interesting, but I mean, okay, let's try this. Okay, let's see if this has any common factors. Okay, so here in this first run, A is 123, B is 51. So A mod B will be 102 is the nearest multiple, right? And if I subtract 123 minus 102, I get 21, okay, which is 123 minus 2 times 51. Okay, I hope I got it right. If I get something wrong, you know, please just say quick so the mistakes don't percolate. Okay. Because I can't look at the chat as I'm doing this. All right. So then the next recursive call is going to be GCD of 51 and 21. Okay, so in this run, A is 51, B is 21, and A mod B will be what? The nearest multiple is 42, and 51 minus 42 seems to be 9, okay, which is 51 minus, again, 2 times 21. 42, yeah, should be 9. Okay, so this is going to call GCD on 21 and 9. Okay, so here A is 21, B is 9, and A mod B is what? 21 minus the next multiple is 18, right? So 21 minus 18, 3. Oh, okay, and we have a non-trivial divisors. Divisor looks like, so this is what? 21 minus 2 times 9. Well, you know, I'm sorry, I picked some numbers. I said this is always 2. That's coincidental. Okay, so this is going to call GCD on 9 and 3. So A is 9, B is 3, A mod B is 0, right? Because it's 9 minus 3 times 3. And do we have a so okay, so now I guess A mod B is 0, so that hits the base case, right? Because A is 9, B is 3, and this code will check if 9 is modulo 3 is 0, yes, and it will return B. So it will already return, it hits the base case, returns B equals 3. So 3 is going to be returned, right? And because in all the recursive cases, so we return B in the base case, right? But all the other cases, they simply return pass. So the output of this call is an output of this call. So this 3 is just passed back from this call back to here, and from this call back to here, and therefore this is going to output 3, right? And okay, you can check, right? Because 123 is a multiple of 3, and 51 is 3 times 17, and also, because 17 is a prime, you can just check that it's not divisible by 17, and you're done. The only prime factor is 3. All right, so let's go back to the slides. Okay, so so you see how this algorithm runs, okay? And well, you can ask questions. So correct, yes, right. See slides. So we argued that the answer to this question is exactly the same as the answer to that question, and also the answer in the base question is correct. In the base case is correct. But you can be, you can, like, people can implement recursion and say, if the first person is correct, then the second person is correct. And if the second is correct, then the third. But maybe this never terminates. So correctness really doesn't mean that you're gonna ever get the answer. Okay, maybe they are in a loop. So, this will never end, even though all these people are correct. But so what? They will never respond, because the first one passes to the second to the third, etc. So you need termination, yes, because basically minimum of B and A mod B is strictly smaller than a minimum of AB. So minimum of these two inputs is your good measure. The minimum of these two inputs in the recursive call is smaller than the minimum in the call. So and A mod B, is greater or always to 0. So you're getting smaller numbers, and you cannot get below 0. So therefore, must terminate. Okay, good. You terminate, so that's pretty good, right? But how about running time? So that is, of course, a very important question, and we'll leave it to discussion. The beauty of this is that it is actually linear in the sizes of A and B. It is not an exponential time algorithm in the description. So if A and B had 200 digits, this will run in a time that is linear in 200. So, I mean, the constant is small. So the number of recursive steps is upper bounded by the logarithm base 2 of these numbers. And you can just take the smaller one. Okay, take the larger one. All right. And it's not immediate to see why that is. But the intuition is that this number is not only smaller, it's actually at least smaller by about a half. So you might see this here. The 21 is smaller than, so we basically, yeah, so 21 is smaller than half of both of these. 9 is smaller than half of both. 3 is smaller than half of both, and so forth. So this is not a coincidence. Okay, and because you slash an input by a factor of 2 every time, so you can see that this is logarithmic in the actual value, integer value, and therefore is linear in the number of digits. If you wrote this in binary, the number of bit digits would be the power of 2, that the nearest power of 2 to these numbers. So if you slash every time by a factor of 2, therefore you remove a bit every time. Okay, and all you need is there so that well, so this takes linear in this bit size of these number of recursions. But how about the time that this computation takes? Maybe this computation is a bottleneck. So you also need to see that how to compute this fast, that it can be computed in a time that is linear in the sizes of these things. Okay, so that's why the running time, which is linear in the length of A and B. Okay, this is a crucial thing because we said, how about instead of computing GCD using this recursive algorithm, you instead fully factorize A, fully factorize B, and look at the their common intersection of these factors and multiply them. But factorization was an exponential time in the length of A. And this guy is not. It's linear in the length. Okay, so that's why this is viable, while you know, the other thing is not. Somebody says, if we wanted to do induction, yes, you should do. Indeed, this is exactly the kind of things that induction allows you to prove any of these, where you know, I'm not proving, I'm just sketching. And the inductive parameter could be the bit size of A and B. Yeah. Yeah, okay, but you know what? Let's, or the number of loops. Okay, so you know what? Let's table that because it's a, yeah, okay. Let's table how this proof would exactly go. It's interesting. I don't know if it's somewhere in the book. I don't remember now, but it is definitely something we can go over at a discussion. Okay. Let me come back to the, okay. So we might extend this algorithm. It's called extended Euclidean algorithm, so that it doesn't only output the GCD, it also outputs two coefficients, S and T, such that the GCD is expressed as a linear function of A and B with these coefficients. In other words, that this equation is true. You will see in the context of a crypto system why it is useful to compute such coefficients. Okay, so I have it here on the slide. It's not perfectly animated, so let's see if I can do this. Okay, so let's take an example of computing a GCD of 259 and 77. And let's just do another run of the GCD, of the recursive Euclid's algorithm, and then see how you would use this run to compute these coefficients S and T in addition to the GCD. Okay. So I'm going to call the initial A and B values in the first call with the A0 as A0, B0. Okay, so A0 will be 257, 259, B0, 77. So I'm calling this algorithm with these numbers, and the first thing it does is that, well, it checks this, but it's not true. 77 does not divide 259. So instead it computes A mod B, which happens to be 28. And why? Because 28 is this difference, and that's the largest multiple of 77 before you hit 259. Okay, so this will be the new B in the new recursive call. So in the recursive call, you're calling it on B and A mod B. In this case, on 77 and 28. So in this next call, your new values A and B will be 77 and 28 respectively, right? I'm going to call them A1, B1. Okay, the integers A, B, which the next recursive call in the next recursive call. Okay, so now we need to compute 77 mod 28, and that's 21 because of this equation. Okay, so that's the nearest multiple of 28. So in the next recursive call, my new A will be 28 and my new B will be 21. And here they are, denoted A2, B2. Okay, so now I do the modular reduction and I get 7, right, because of this equation. All right, and so this will be my new A, 21, and 7 will be my new B. So that's A3, B3, but that's we hit the base case now because 7 divides 21. So this will be a base case. So we return 7, and you can check that that's correct, right? 77 is 7 times 11, 259 is 7 times 37, and 11 and 37 don't have common factors. Okay, so far so good. Let's see, where do we get S and T? Okay, so let me represent this run as follows. You see, I'm going to focus on this table. So you see, as I computed, let's not forget these middle computations that happened at every step. The computation of this GCD involved expressing the remainder from this integer division as the number I divided minus some number of multiple of divisor. And that's always the case, right? Like these are linear relations that express the remainder as some linear function of the number I divided times and the divisor. So because the GCD, and look, this GCD, and at the end of this, my last number here is the GCD returned, because at the end of this chain, this is the B that gets passed to the recursive call. And if that is the base case, then that is the GCD. This B was the GCD. So the last guy in this writing is the GCD. And look at the following invariant. At every line, the new B is a linear function of the A and B. So the new B, which is 7, is a linear function of 28 and 21. In the next line, the new B, which is 21, is a linear function of 77 and 28. What this gives. And here, the new B, 28, is a linear function of 29 and 77. We can use this linearity. So we express the final equation expresses the GCD as the linear function of the A and B in that call. But we can combine it with this so that the final GCD is also a linear function of the A and B on the next call up. And then we will use that to express the GCD as a linear function of the next level A and B. And because this is the final one, so first of all, this will work any number of steps that we want to go up, and therefore it will reach the final one, and at which point the coefficients in this linear equation will be coefficients S and T. Okay, let's look at how this works at this example. So I'm going to take these equations and copy them because they are the ones I really care about. And so the final thing is a linear function of the previous. And okay, I'm going to arrange my A's and B's on a line, because if you notice, this guy is just a copy of this, and this is a copy of that. So I might basically disregard these. The interesting thing is starting point and these guys, okay? Because these are just copies. So here are my. Someone is trying to say something, but I'm not sure what. All right. Okay. So here is how you reverse this. Use these linear equations to express 7 as a linear function of 259 and 77. So your original A and B. So the final equation already tells you the coefficients that are needed when if you want to express 7 as the last A and B. So as a linear function of the last A and B, 28 and 21, right? The coefficient here was 1, the coefficient here was -1. Okay, it doesn't have to be -1, it could have been some other multiple, but it just happens to be -1 here. Okay, but now I can use this equation to plug in basically to remove 21 from here and replace 21 as this linear function of 77 and 28. If I do that, then I get this equation. So 7 is 28 minus 1 multiple of 77 minus 2 multiples of 28. This minus became a plus, and I had 1 multiple of 28 here, and I essentially added 2 multiples of 28, so I got 3 multiples of 28. Okay, so these two equations, the useful way of combining them is so that to express the final GCD as a linear function of the next two A's and B's, which is 77 and 28. And the way I do it is just I have to express, because of this equation, I can express 21 as a linear function of these two. I stick it in here, and I get 7 as a linear function of 28 and 77. And then I recurse. And so now I express GCD as a linear function with some coefficients of the higher level A and B. And these coefficients turn out to be these, -1 and +3. And now I recurse. I now do this, I use the same procedure to, so at that point, I express this GCD as a linear function of these two. And I want to express it instead as a linear function of these two. What do I need to do? Kick out the 28 and use this equation to express 28 as a linear function of 29 and 77. And then stick this inside of this equation. Replace 28 by this linear function of 359 and 77. Then I will have some multiple of 77 here, some multiple of 77 here, and some multiple of 259. The two together will express 7 as a linear function of 259 and 77, and that's what happened here, right? I have, yeah, okay. So this is the result of that substitution, and okay, so it happened to be 3 and -10, and right. So this is the algorithm. You can go up, follow the same way of substituting, but this is the logic of the algorithm, right? If you go up the layers, at every point you express the final GCD as a linear function of sum of A and B on some level, and you use the fact that the next that 21 is a linear function of the next A and B to take the two equations and end up with expressing 7 as a linear function of the next A and B, and so you recurse. Okay. I'm not positive that I rendered this algorithm in the best way, but I hope. Okay. So I don't know if I'm over laboring it or losing it. Let me end this segment with an application of this extended Euclidean algorithm. So with one application. So if in the modular arithmetics, we are now going to introduce the notion of a multiplicative inverse modulo n. So I'm going to call, if you have two integers mod n, this set is an important notation that you should learn. Integers reduced modulo n, that stands for the following set. It's the set of all remainders of integer division mod n. So it is integers from 0 to n-1. Okay, I will call integer b in this range and multiplicative inverse of a in this range mod n if the following is true. The two integers multiplied give a 1, but the multiplication is mod n. If that is true, then I will denote b as multiplicative inverse as a to the power -1. All right, because it's 1 over a. So this is a multiplicative inverse. If you take a to the power of -1 and multiply by a, the two powers -1 and 1 add to 0. So the result is a to the 0. So that's a 1. Okay, so you get that. So let's recall the multiplication table in Z5. What is the multiplicative inverse of 2? It's a number such that if you multiply 2 by it, you get a 1. that number is 3. Okay, and you can check 2 times 3 is 6, which mod 5 is a 1. What is the multiplicative inverse of 3? Well, clearly 2. It's symmetric, right? If B is a multiplicative inverse of A, then A is a multiplicative inverse of B, right? Because it's a symmetric relation. What's a multiplicative inverse of 1? Well, that's a trivial thing. It's always 1. What about 4? Well, there is a number that multiplied by, if you multiply 4 by something, you get a 1. That something is 4 itself. Check. 4 times 4 is 16, which mod 5 is 1. So turns out every element in Z5 has a multiplicative inverse except of 0. 0 cannot have a multiplicative inverse, right? There is no integer such that if you multiply 0 by it, you get a 1 in a modular arithmetics, right? So 0 has no multiplicative inverse, but everything else does. Okay. Now, when you try to do the same mod 6, it doesn't quite work. So multiplication mod 6 is not a permutation. This row of multiplication by 6 does not show every element here. In particular, does not show a 1. In other words, there is no integer such that if you multiply 2 by it, mod 6, you get a 1. And that's intuitive, because if you multiply 2 by anything, you get an even number. And if you do modular reduction by 6, an even number it continues being an even number, because you take modular reduction by an even number, 6. So you cannot get a 1. Similarly, if you multiply 3, the only possible remainders of products of 3 are 0 and 3 if you do mod 6, right? Because 6 itself is a multiple of 3. So you can either have even multiples of 3, which will basically multiples of 6, therefore mod 6 is a 0, or an odd multiple of 3, which mod 6 is just going to be 3. In particular, there is no 1. So mod 6, a lot of integers here don't have multiplicative inverses. Only 1 and 5 does. Okay. Okay. So here is a very useful fact. A has a multiplicative inverse mod n, even only if A and n are relatively prime. They don't have factors in common. In other words, if GCD of A and n was 1. So this is why everybody here had none of these guys had factors in common with 5. Why? Because 5 was prime. And therefore, everyone had a multiplicative inverse. Here, 6 is not a prime. Exactly the numbers which were not coprime with the modulus, 2, 3, and 4, were the ones where this table does not have a 1, which means these were the ones who had no multiplicative inverses with mod 6. But 1 and 5 are coprime with 6, and they had multiplicative inverses. There was a 1 in the row. Okay, so okay, so you can justify this by looking at by the Euclidean algorithm that that if two numbers are relatively prime, then they will have multiplicative inverses, and the proof of it is the existence of these coefficients. And if two numbers are relatively prime, therefore the GCD is 1. But by existence of the extended Euclidean algorithm, you see that there must be coefficients S and T, which will make this true. right? That just follows from the extended Euclidean algorithm that they exist, and moreover, extended Euclidean finds them. This coefficient here is a multiplicative inverse of x mod n, because, okay, so here's an example. Okay, I'm going to verify that 79.9 and 59.54 have GCD1, and the Euclidean algorithm will find me these coefficients. And now minus 19 is the multiplicative inverse of 54 mod 79. And but I don't like to express the multiplicative inverses as negative. I want to express them as numbers mod n in mod 79. So it's a 60. Minus 19 mod 79 is a 60. This 60 is a multiplicative inverse. And now in general, why that is, okay, it is because t times x okay, I'm trying to rush, and because I know I'm going slightly over time, and unfortunately I called t here b. Anyway, cutting down to the chase, it's t times, if this equation is true, then just move Sn to the other side. T times x is 1 plus some multiple of n. And therefore, if you reduce it mod n, then t times x is a 1. Because mod n, this part vanishes. So it is true that t times x is 1 mod n. And that is the same as to say that t is a multiplicative inverse of x mod n. Okay, that's all this thing says. So not only you can use Euclidean to check that two numbers are relatively prime, or to compute their GCD, their common factors, but also you find multiplicative inverses of integers modulo in modular arithmetics. And we'll see in crypto systems why we care about these multiplicative inverses. Okay, sorry for going over. Do you have, if you have questions, ask them now.
Thank you, Professor. Have a nice day.
Okay, thank you.
My question is, so like, what are the applications of like finding the GCD or using the extended Euclidean algorithm? Like, is it all for cryptography?
No, I'm sure there is others. So coding, like error correction codes, hashing, you know,
like the main like applications would be like.
It's actually, I'm sure there's more applications, and
Okay.
I'm just blanking on them right now. But in cryptography, there's tons. Basically, cryptography uses modular arithmetics. Okay, not only. So there's other cryptographic settings of cryptographic use which don't exactly use modular arithmetics. And but there are many applications of modular arithmetics in cryptography. And so multiplicative inverses will be computed in there. And we'll see that. So possibly next lecture already.
Okay, yeah, great. Thank you.
Okay. So yeah, if there are no questions, I will quit now. I'll see you Friday, and you will get an email when I post the homework on that stuff. All right, and it will be later today. Thank you so much. See you next. Yes.
Do you have a second to meet separately so I can talk to you about the practice test for test number 3?
Yes, but maybe we should do this on some separate.
Oh, yeah. We can do that separately. Do you want me to send you a link?
Yes, but let's talk later today, because I actually have to go off now to
Okay.
another thing.
Okay, no worries.
Okay. Talk to you well. Thank you.